started. So firstly, there's a lot of people here. I imagine that this is not going to be very relevant and maybe rather advanced for some of you as a disclaimer. But the point of this demo is to show how easy it is to build neural networks in Python using PyTorch, and to explain a little bit more about how neural networks work under the hood, and to give you a base to understand more advanced neural network architectures. And also to show you a little bit about what PyTorch, which is one of the largest and most widely used deep learning frameworks, can do. So I imagine a lot of you are here because you've heard about neural networks and are excited to understand a little bit about how they work. But before we do that, I also need to point out what this demo is not. So this demo is not an introduction to machine learning. I will not be going through that. It is not going to be a showcase of any best practices in machine learning. So I'll be leaving out a lot of stuff just purely because that's not the focus here, but it is stuff that you should do if you're working on any real applications. I'm not here to teach the maths behind neural networks today. And I'm not here to implement any state-of-the-art neural network architectures. I'm going to do a very simple example, and there are very complicated architectures which do all of the interesting stuff out there. Finally, I am absolutely not demonstrating what a job in data science looks like. I'm absolutely not doing that. In almost all cases, what I'm going to show is something that data scientists spend zero time doing. So if you're excited by this demo, don't take that as a sign to say, oh, I want to go and be a data scientist, because this is really not what the job is. But for people who are working in, in very particular companies, on problems which require you to be able to model complex relationships between data, and you're in a very specific team, then you might be doing something like this, or at least a smaller part of this on a more complicated system. But yeah, those are my disclaimers for today. I'm wondering if I'm going to see like half the room empty now. No, we look good. All right. But what are we actually going to do? Well, what we're actually going to do is I'm going to explain a little bit about neural networks. I'm going to implement one in Python. And then really I can take this demo wherever we want to go with it, really. So we'll have like a vote and a conversation at that point to see what we want to do with it. But we can either try and visualize that same neural network in a bit more detail. We can try to solve a problem for a different data set, maybe our own data set, rather than the one I show the demo. Or we can go on to talk about something more advanced, perhaps convolutional networks. Or we can go in the other direction and talk more about what's underlying what I build here, maybe talk about the mathematical details, but it depends on you guys. So we'll see. We'll also see where we get to, because I have a habit of constantly underestimating how long things are going to take. But I think we can get through it today. Any questions or anything before I go on? Cool. Well, firstly, before we get into the code and some examples, what is a neural network? To describe it in one sentence, I would say that neural networks are machine learning models that build hierarchical representations of data to learn to represent any input-output relationship. So one more time, they're machine learning models that build hierarchical representations of data to learn to represent any input-output relationship. So to break that down into those three parts, machine learning models, hierarchical representations, any input-output. Starting with machine learning models, well, what does that mean? It means that they're a mathematical function that takes in an input and produces an output, much like the functions I'm sure many of you have worked with in math, or the functions that you are writing in Python, which take an input and return an output. And that mapping between the input and the output is controlled by some parameters. If I have a function which is y equals 3x plus y, 3 might be one of those parameters. And those parameters can be adjusted. And adjusting those parameters changes what that function does. It changes the relationship of the input to the output. What comes out when I put in a different input depends on what those parameters are. And we call that function a model. And we call the process of the computer adjusting those parameters, which adjust that function, we call that process learning or machine learning. So yes, neural networks are machine learning models. The second thing, which I said, is that neural networks build hierarchical representations of data. So what I mean by that is that they're different to a lot of other machine learning models in the sense that they build these representations which build upon layers of understanding. So instead of trying to go directly from the raw data to making a useful prediction, might be, the inputs of self-driving car, outputs are the acceleration and direction, or the inputs are all the songs you've listened to recently. The prediction would be what song do you want to listen to next. Instead of going directly from that raw data to a prediction, neural networks will go through not just one mathematical transformation, but several in layers. The first layer, you're learning something which is kind of, still rather abstract. It's a very big set of numbers which represent lots of things which you might not understand exactly what they mean. And then beyond that, each layer represents a transformation of that previous layer to combine them gradually into more and more meaningful concepts, until at the end of all of those layers, you've got a set of numbers which represent something which actually make quite a lot of sense intuitively. It might be like, okay, how much does Ivan like rock? Or, how popular is he into, how much is he feeling the K-pop lately, or something like that. And those are kind of, much more high level, meaningful pieces of information. Whereas the raw data was like very hard to understand. It was just, 1,000 different songs. It wasn't in any way, categorized or condensed into the actual meaning of why he'd listened to them. So that's what I mean by these hierarchical representations. They build on top of layers of understanding, which get more and more high level and meaningful. That's the second part of my definition. And overall, all those different layers are just, they're just simple functions repeated one after another, and combined together, they represent a much more complex function. The final thing I said was that they can represent any input-output relationship. It's kind of remarkable, and I won't go into it, but mathematically, you can prove that these models can approximate any continuous function, which is between the inputs and outputs. So really the relationship between any two variables can be modeled with some mathematical function. It's just a case of finding that function. And the key point there is that these neural networks are, you might hear them referred to as universal approximators. So they can approximate really any function, any continuous function. Like I said, I'm not going to get too much into that now. I hope that's at least some more understanding on what these kind of mathematical functions, which can do all this impressive stuff like speech transcription or self-driving vehicles or ranking the feed on your Instagram ad. Those are all kind of some of the things which are powered by neural networks. And that's exactly why I wanted to run this demo, is because if you didn't know, basically all of the breakthroughs in AI that have happened in the last decade are a result of neural networks. All of the stuff which really just wasn't possible before, all those examples I've mentioned, a lot of them are the result of these types of machine learning models. So to actually show a few, I will share my screen and go through some examples. So the first one being AlexNet. This back 10 years ago, actually was, it's been a whole decade now. 10 years ago, this thing which is called AlexNet, it's destroyed the benchmark for computer vision in the ImageNet competition, which is the competition benchmarking the performance of computer vision models. And this is the first neural network diagram you might see. And what it represents is, this is an image which comes in. It's, I believe, an image comes into there. somewhere on here. And then what it does is it applies some mathematical function, basically just a matrix transformation, to change it into this shape and combine each of these different values in this matrix in different ways to produce a different shape. And this one has smaller height and width, but it has more channels, has more thickness here. I realize this one's not the image because it has 96 different channels. So the image must come in here. Images typically have 3 channels, red, green, and blue. And then that image will be transformed by some matrix multiplication into this shape, which represents a combination of those features. The combination of features represents something more meaningful, something more complex. Then we do the same thing again, combine those individual features from this layer in a way which will give us something more meaningful and more complex in this different shape, which is now smaller. So we're condensing the information and combining features into more complex concepts as we go through this model. And at the end, we flatten out these big, they're not actually matrices, they're tensors because they've got height, width, and depth. And we flatten them out into vectors, and then we just do vector multiplication. And then, this is again, just more vector multiplication until we have this final vector of 1,000 different numbers. The ImageNet competition is, the aim of it is to do a 1,000-way classification. So you get images, they're one of 1,000 different classes, and you need to output a vector which has the largest number for the true class. Each of these numbers in here is actually representing a probability. So it's the probability that you think that this image, which came on the left, is a member of that particular class. So that's this kind of where, this is the point which everyone refers to as the beginning of the deep learning revolution, which was when AlexNet won the ImageNet competition. So that was kind of the first neural network to really hit the headlines. You'll notice one thing, which is that these are not vectors, these are tensors, like I said, and that's because this is a particular type of neural network called a convolutional neural network, which doesn't just work with vectors like the network we'll see today does, but they work with images and other kind of spatial data. Okay, cool. So that's the first example. And we've come a long way since then, all the way to a lot more complex models, such as Mask Rcnn, which is a rather well-known computer vision model. This one doesn't just do classification, it does what's the way to say it? It does multi-instance segmentation. It does instance segmentation, basically. It looks for different instances of different classes, and it segments them by drawing an exact pixel map of which pixels correspond to particular instances of objects of interest. And you can see it's doing that not just for one class, not just for one instance, but many instances of many different classes. You see I've got 2 different instances of traffic lights, many different instances of the cars. And so that's a much more complex problem than just doing the basic classification. Yeah, this is called Mask Rcnn. You can take a look at this thing, just search Mask Rcnn, it will come up. You can kind of see what it does. It produces a load of bounding boxes of regions of interest, and then it goes through the process of classifying them, and then it goes through the process of generating these masks, which are then overlaid on top of those instances so that you get an exact pixel-wise outline of each of them. So yeah, so that's kind of where we come in terms of computer vision. I'll actually show that one last. Another one you might have heard of is Alphago. This is a neural network which beat the Go grandmaster. It was, again, a convolutional neural network. I highly recommend watching this documentary. It's really great. It's about how they built the algorithm and then how they built the champion, Lee Sedol. It's really incredible. But basically, Go is a very complex game, a board game, and and nobody thought it could be done, and they did it with the neural network. And then they built AlphaZero, which did the same thing, but varies in two interesting dimensions. One is that it requires no initial data. It learns totally from scratch, which is why it's called AlphaZero. They simply put it in a simulation, running these games, and it generates all the data and all the experience which it needs over time, and learns to destroy not just Go, this is the other interesting dimension, but many other games, chess, shogi, and a few others, I think. Another point, maybe interesting to mention here, and why it talks about shedding new light, is because this model was trained with no labeled data, which kind of had the prior, which had the prior experience of a human injected in. It learned everything for itself, and what that meant is that you see this model perform what seem like creative and original moves, even though it came up with them totally on its own. It's a machine that did that. But yeah, there's a very famous move in the AlphaGo documentary, like, what was it, like move 67 or something like that, and everybody was shocked when they saw it. They were like, oh, look at it, haha, it's done something very silly. No human would ever do that. And then a few moves later, you realize that, wow, it's thinking 10 steps ahead. Another few interesting neural networks from DeepMind, and then one from OpenAI. You may have heard of GPT-3, Generative Pre-trained Transformer version 3, which predicts the next sentence, or predicts the text to continue with a prompt. So you give it a prompt, and then it fills in the rest. So this is what's been predicted by that neural network. And so my AlexNet to Mask Rcnn examples, they really show how kind of neural networks have unlocked the domain of vision and have allowed for massive automation there. And GPT, or more generally, the transformer architecture of neural networks has and really is starting to unlock the domain of natural language, which there of course is a huge application for, because there's so much data for it. So yeah, I highly encourage you to check these out. You can see some of the other things it can do. For example, you can give it a prompt followed by something you want to summarize, and then it will do that. And this model, the paper announcing this model, it won the Best Paper award at the biggest machine learning conference, with the title "Large Language Models Are Zero-Shot or are Few-Shot Learners." And what that meant was that in just a few shots, with just a little bit of training, a pre-trained language model can accomplish many different tasks, not just predicting the next sentence. So by giving it a prompt, you can actually get it to do insanely impressive stuff like translation, all with the same model. Very impressive. So is there any questions about that? Cool. Well, what we're going to do then is I'm going to open up a new file where we're going to make our own neural network, which is why I called it nn.py. So what we're going to do is we're going to use a library I mentioned in the title of this demo, which is PyTorch. So let's take a look at what that is firstly. Just up, as we know to do. Okay, PyTorch here. What is it? An open source machine learning framework that accelerates the path from research type prototyping to production deployment. If we go back, we might get another definition. Yeah, it mentions computer vision, natural language processing. Basically, it's a framework for building deep learning models. Neural networks are the canonical deep learning model. Deep learning just means machine learning model, which is deep and has many layers, if you didn't already know. There's many tutorials and stuff you should look at here, and there's many resources on the portal which you can look at as well. But for now, I'm going to assume that we know how to do this, and I'm going to take you through it. So I'm going to import Torch, which is the name of the library, and I'm going to try and create here my own neural network. I'll talk you through the steps as I'm going. PyTorch is rather complicated, so don't freak out if you don't understand all of this immediately. And also, the code which I'm going to write covers up a lot of complicated math, which, like I said, I'm not going to go into now. I will explain, or at least I'll say what it means, but I probably won't go into the details of how that maths works just because we don't have time. But feel free to catch me after if you like. So typically, the way that you implement machine learning models is by writing a class, and I'm going to call it NN for neural network. And just to do a rough little outline of it, I'm of course going to have a initializer, and then down here I'm also going to have a method which I'm going to call forward. What this one's going to do is it's going to take in the features, and then it's going to return some prediction. Okay, and we'll fill that in here as we go. All right, so that's the idea. We're going to create some neural network. It takes in some data, makes a prediction, and we have to implement some code around that. But the first question is, what actually comes in here? What are the features? And what is the data set that we want to work with? Of course, it's up to you. Depends on the application. But thankfully, PyTorch provides a range of kind of toy data sets in its computer vision library. So there is another library developed by the same people, which is Torch Vision. And actually, I'll do from Torch Vision import data sets. And so then I can get a data set, which will be dataset dot, and here you can see all the different data sets which they provide, which is kind of nice. MNIST is is basically the welcome to deep learning data set. It's a data set of I think 70,000 28 by 28 pixel images of handwritten digits from 0 to 9. So this is a class which I'm just going to initialize, and it takes some keyword arguments like root. So this is where it's going to save it. I'm going to do mnist -data, and what else does it take? It takes in the keyword argument download, which will download it off the internet if it doesn't yet exist. You can see the other arguments there. It takes train, so I'm going to get the training set, not the testing set. What else does it take in? Nothing for now. We won't worry about that. And then yeah, let's print the data set and take a look at that. And I'm going to put all of this in different cells so we can break up our code nicely. Cool. So I'm going to run that. All right, so it's downloaded the data into here, this mnist data file, which I specified, and I printed it, and it just says this. It says, okay, number of data points 60,000. The full thing contains 70,000. There's 10,000 in the test set, but it's in this folder. Cool, looks good. But I actually want to see the example. So now, can I iterate through it? So let's say from data point in data set, print the data point, and then I'll just break. So I just get one of them, I'll run that, and I'll move you guys out of the way. And down here, we can see what it has printed us. So it's printed us this thing. That is a tuple. It's a tuple of two things. The second thing is an integer, 5. And the first thing is this. It's a pill image. So I know that pill is the Python image library, and that means that I should be able to show that image. So firstly, I'll unpack that data point into the image and any guesses what the 5 is? Of course, it's the label. It's going to be an image of a 5, although this will probably be shuffled the next time I do it, I think. But yeah, let's just unpack that data point into those two things, and then do image dot show and see if that shows us an image. There it is. So there's a 5. Not very big. That's what it looks like. It's 28 by 28, only one channel. That means it's grayscale. There's no red, green, and blue channels. It's just got a grayscale channel. But that's what our data looks like. It's a matrix. So with that, now we kind of understand the data a little bit, right? And what that means is that we're kind of more ready to start kind of putting that into the neural network. So how would I do that? How am I going to use this later? Of course, I'm going to implement a instance, my neural network, which is an instance of that class, neural network. And what I'm going to do with that eventually is, I want to be able to make a prediction. So I want to essentially do dot forward on that with some image and then get a prediction. That's my outcome here. So that then when I put this in the real world, maybe I'm working, trying to transcribe handwritten digits on forms. I've got some software which is going to do that for me. I want to be able to make those predictions accurately all the time. So that's how I want to be able to use this at the very end. So, so what should we do? What should we do now? We've got, okay, well, let's implement the body of the neural network. So this neural network, like I said, it's just a mathematical function which is going to depend on some parameters. And that's what we're going to implement in here. We're going to initialize those parameters when we initialize the model. They're initially going to be random, so it's not going to do anything useful. And then what we're going to do is we're going to do the machine learning, the process of updating those parameters so that they become more and more correct, so that each layer represents something more and more useful. And eventually the final layer will represent, is this a 1, is this a 4, and be able to help us with those predictions. How do I do that? Well, firstly, let me say, you might have heard of another machine learning model, the welcome to machine learning model, which is called linear regression. And what that is a mathematical function which takes in a list of different features, which are numbers, aka a vector mathematically, and it weights each of them and then adds them up. It's basically it's what's called a linear combination. It's a weighted sum of the features. So you might be trying to predict the house price. You got a vector of 3 things come in. It's the age of the house, it's the age of the person who lived there, and it's the what's my usual example? And it's the number of bathrooms, something like that, right? So you got those 3 features. That's a vector of 3 different numbers, and you're trying to predict the house price. So each of those 3 different features have some different importance. The age of the house, well, how is that going to affect the output? Probably, I don't know if this is true, but let's say the older the house is, the less the house is going to be worth. So what you might expect is that the weight of that parameter is negative. That means the bigger that number, it's going to be multiplied by a negative, the older the house, the bigger that feature, the less the price. So what you want to do is weight that feature by a negative number, so that as the age increases, more and more is subtracted from the final house price, because the house price predicted is going to be the sum of each of those different weighted features. The second feature I said was the age of the person who lived there last. Now that feature, it shouldn't make any difference on the price of the house. So you'd imagine the weight of that feature is roughly or exactly 0. And then the final feature I mentioned was the number of bathrooms. So more bathrooms, probably going to be worth more. So the weight of that feature would be large. And that's how a linear regression model makes predictions, at least. It has a weight, which is associated to each feature incoming, and then it adds all of them up. So the weights really indicate kind of the importance of that feature in increasing the output. And all a neural network is, not to get into too much detail here, but all it is lots of those similar weighted combinations stacked end to end. And so each of them represents a different layer. We're combining the features in some way to make some more meaningful combinations of them. And then we're taking those more meaningful combinations and then combining them again, and then again, and then again, however many layers we have, so that through each layer, we get a hierarchically more complex, high level, meaningful representation of the data until we're at the point where in the final layer, we can directly make a prediction because they represent something nearly to like what we actually want out as our final output prediction. So that is what I'm going to implement here. I'm going to say self.layers, and I'm going to run through this quickly because there's a lot of stuff here, and don't want to get too into the inner workings. But self.layers is going to be equal to torch. Okay, it's got a neural network module, and it's got something in here called sequential. This is basically going to allow me to specify the sequential layers of the model. The first one is going to be a linear layer, just like in linear regression. And it takes in, this is a class which I'm going to call the data on. I'm basically going to pass it through all these layers. It's going to come into here, so come out the other side, and then that's going to be returned as my prediction. So I'm going to put some more stuff in here in just a sec. But just to illustrate how I'm going to use this, I'm going to say prediction is equal to self.layers of the features. Okay, so features come into the layers. The layers are specified here, and it's basically a series of different transformations which I'm going to do on the data until I get to the end of everything that's in here. And finally, that's going to produce me a prediction. So I need to specify those series of linear transformations, and they are written like this. So I'm going to have several of them basically written in here, something like that, right? So this will be like a 5-layer neural network, and each of these things, this is a class, right? It's a class which, when I instantiate, it's callable. So I'm basically going to get this thing, I'm going to call it on the incoming data, and then I'm going to get this thing, and I'm going to call it on the output of this, and then I'm going to get this thing, and I'm going to call it on the output of this layer, so that sequentially will pass the data all the way through these layers until the end. Each of these linear layers contains the weights, which each of the incoming data will be multiplied by before being added up and then coming out the other side. So one thing that I need when I specify these linear layers is how many values are coming in. Well, in this example, we're going to implement a very simple neural network, what's often called a fully connected neural network, which they only process vectors. They don't process any more complex data like a matrix or a tensor or an image or a video or an audio waveform. They're just going to process a vector. So whatever data that I am bringing in, I need to convert it into a vector firstly. I know that my images are 28 by 28 by 1. There's only one channel because they're grayscale. And so that means that if I flatten out that image, it's going to be 28 squared. I've done this many times so that I know 28 squared is 784. So that's how many items there are going to be in the incoming vector to the first layer of this network. And here, after this, I need to specify how many outputs is this linear layer going to have. It doesn't just have to have one. It doesn't have to combine all the features into one single output. It can combine them in many different ways to produce many different outputs. And really, there's no real science to this that's really confirmed and been adopted widely yet. So you can kind of just make it up yourself. But the rule is use powers of 2 so that you don't have an infinite kind of architecture space. So I've said this layer is going to take in a vector of 784 items. It's going to combine them in 1024 different ways. And then I'm going to go from there. So this layer needs to take in the output of the previous layer. So it needs to do 1024. And then I'm going to start, I've actually made it like bigger here. So I've kind of allowed space to create 1024 different features out of the original input features. So I'm combining them in different ways to create a more complex feature. But now I'm going to start narrowing it down. So I'm going to go from 1024 to I'm going to go to 512, and then I'm going to go from 512 to 256, and then I'm going to go from 256 to 64, and then finally I'm going to go from 64 to 10. Why have I chosen 10? given that that's the last layer of my network architecture. Any guesses quickly? 5 seconds.
Because of 10 outputs.
10 outputs, exactly. Thank you, Laura. 0 to 9. So the thing which comes out of this is going to be a vector which contains the probabilities of each of those different classes, essentially. So that's my architecture. However, there is a problem here, which is that if I just do 5 linear transformations, they're actually equivalent just to 1 linear transformation. So I need to add something in the middle between each of these, which is called an activation function, which is really any nonlinear function. It just means that the whole thing can't be collapsed into a single linear transformation, i.e. a weighted sum. So the typical one to use is what's called a Relu. It's a very simple function. Yeah, I won't explain it here, but you can go look it up. But that's it. That's the architecture of a neural network. That's exactly how a simple one looks, and that's fine. But yeah, this activation function, just any nonlinear function, typically use Relu or tanh or sigmoid or something like that, but almost always Relu these days. Okay, the final thing I need in this is that, well, actually, let me explain something to lead to that. So if I output a vector of 10 numbers, I want those numbers to represent the probabilities of the different classes. And so that 10 vector needs to be a probability distribution. It needs to have certain properties if it's a probability distribution. It means that none of the probabilities can be negative, because it doesn't make sense to say something's going to happen with negative 0.5 chance. So they all need to be positive, and they all need to sum to 1, because overall, I can't give out more than 100% confidence across all of those different options. So there is a mathematical function which does that for you, which Torch includes as well, which is called not the sigmoid. What am I thinking of? I'm thinking of the Softmax, right? Yeah, I'm thinking of the Softmax. Rcnn.softmax. That is a function which will basically turn this vector into a probability distribution. So now self.layers are going to do all those things, and then that's going to make a prediction. Okay, so we're getting somewhere. That's the network implemented. Anything I'm missing? No, let's keep going. So I should be able to run this now, and we'll get an error and we'll fix it, and then we'll go forward. All right, cool. There's an error here. Let's try and read it. It says linear argument input must be what does it say? It says must be a tensor, not an image. Why is it an image? Well, if we think about it, we know that our data set actually contains these images. These are pill images. So what